Good afternoon, all. In the previous lecture, we seen that what is the orthogonal set and orthonormal set. Okay, so today we will discuss what is the orthogonal complement. Okay, let's see the definition. Let V be an inner product space and S be any set of vectors in V. Okay. Let V be an inner product space and S be any set of vectors in V. Then orthogonal complement of S is set S complement. Okay. This is read as a S per or S perpendicular or S complement. So set S complement of all vectors in V. Okay, this notation we read as a S perp. Okay, of all vectors in V which are orthogonal to every vector in S. Okay, if V is the inner product space and S be the any set of vectors in V, then orthogonal complement of S is a set S per of all vectors in V which are orthogonal to every vector in S. Okay. Thus, we can denote S per is the set such that alpha belongs to V such that the inner product of alpha and beta is equal to 0 for all beta belongs to S. Hence, the inner product of alpha and every vector of S becomes 0. Okay. So next point is that the theorem on this. Okay. Let S be any set of vectors in an inner product space V. Okay. Let S be any set of vectors in an IPS V. Then S per is a subspace of V. We have to show that S per is a subspace of V. Let alpha and beta belongs to S per be any two vectors. Okay, let alpha and beta belongs to S per be any vectors and C be the any scalar. Okay, so then we have alpha, the inner product of alpha with gamma is equal to 0 for all gamma belongs to S by the definition of S per. Okay, what says the definition? The inner product of alpha with gamma is equal to 0 for all gamma belongs to S by the definition of S per. Give it as equation number 1, and also the inner product of beta and gamma is equal to 0 for all gamma belongs to S since alpha and beta belongs to S per. Okay, give it as equation number 2. Now for any gamma belongs to S. Okay, for any gamma belongs to S, consider the vector C alpha plus beta, and taking inner product with gamma, we have C into inner product of alpha gamma plus inner product of beta gamma. But alpha and beta belongs to S per. Hence the inner product of alpha and gamma is 0 and beta and gamma is also 0. Okay, from equation 1 and 2. Hence, the inner product of C alpha plus beta and gamma is equal to 0 for all gamma belongs to S. Okay. Hence, by the definition of orthogonal complement, the C alpha plus beta belongs to S per. This whole vector belongs to S per. Since the inner product of C alpha plus beta with gamma is equal to 0 for all gamma belongs to S, then by the definition of orthogonal complement, C alpha plus beta belongs to S per. Hence, for any alpha beta belongs to S per, we show that C alpha plus beta belongs to S per. Hence, the condition of subspace is fulfilled. So, S per is subspace of V. Okay, for any set V, yes, sir, for any set in V, for any set yes in V, yes per is a subspace of V. Okay, so one note is there, the singleton zero. Suppose yes is the singleton zero. Okay, so singleton zero per is equal to V. Why? Because since The zero vector is the orthogonal vector to each and every vector of inner product space V. Okay, since 0 is the only vector which is orthogonal to whole V, inner product space V. Okay, suppose S is equal to V. Okay, then V per is equal to singleton 0. Why? Because 0 is the only vector which is orthogonal to each and every vector of an IPS V, inner product space V. Okay, so 0 per is equal to V and V per is equal to singleton 0. Okay, now, S perp is always non-empty. Okay, so at least one vector is exist in S perp. Okay, why? Since 0 is perpendicular to every vector to S, hence 0 is belongs to S perp always. In the subspace S perp, 0 is always there now. Hence the 0 belongs to S perp always. Hence S perp is always non-empty. Okay. Then the next point is that orthogonal projection of B on W. What is the orthogonal projection of B on W? Let W be subspace of V. Okay. Let W be the subspace of an inner product space V, and let beta be any arbitrary vector in V. A best approximation alpha to beta by vectors in W whenever exist. It is called orthogonal projection of beta on W. Hence, in the previous lecture, we seen that what is the best approximation. Okay, using that definition here, let W be the subspace of V and let beta be the any arbitrary vector in V. A best approximation alpha to beta by vectors in W whenever exist, then it is called as orthogonal projection of beta on W. Okay, so this is the definition of orthogonal projection. Whenever the best approximation of alpha to beta exists by vectors in W exist, then it is called as the orthogonal projection of beta on W. Now, the orthogonal projection of V on W. The next definition is orthogonal projection of V on W. If every vector in V has orthogonal projection on W, if every vector in V has an orthogonal projection on W, the mapping that assigns to each vector in V to its orthogonal projection, that is best approximation. Okay, on W, it's called the orthogonal projection of V on W. Okay, if every vector in V has an orthogonal projection on W, the mapping that assigns to each vector in V its orthogonal projection on W is called as orthogonal projection of V on W. Okay, the orthogonal projection is nothing but Sauli. In Marathi, it is Sauli. Okay, note. By third statement of the above theorem, the orthogonal projection of an inner product space on a finite dimensional subspace always exists. Okay, on any finite dimensional subspace, there always exists an orthogonal projection. Okay, second statement. If E is an orthogonal projection of V, if E is an orthogonal projection on V onto W, that is E is the mapping from V to W, then E of beta equal to beta for all beta belongs to W. Whenever beta comes from W, then E of beta is nothing but beta for all beta belongs to W. Here the W is the subspace of V. Okay, here, W is a subspace of V and V is the inner product space. That is, the orthogonal projection on E on V acts as an identity operator or identity mapping for the elements of W. Okay. For orthogonal projection, E on V acts as an identity mapping for the elements of W. Okay. Then the next theorem is that let V be an inner product space. Let V be an inner product space and W is the finite dimensional subspace. And E the orthogonal projection V on W. E is the orthogonal projection V on W. Then the mapping beta to beta minus E minus beta. Sorry, beta to beta minus E of beta is the orthogonal projection on V on W perp. Okay, this is W perp. And this mapping beta to beta minus E of beta is orthogonal projection on V on W perp. Okay, let us see the proof. Let W be the finite dimensional subspace of an inner product space V and E be the orthogonal projection of V. Okay, and E be the orthogonal projection on V of V. That is, for each vector beta belongs to V, a vector E of beta belongs to W is the best approximation to beta by the vector in W. Okay, for each vector beta belongs to V, a vector E of beta belongs to W is the best approximation to beta by vector in W. Then, by first statement of the previous theorem, we have beta minus E of beta is the orthogonal to W. Okay, so beta minus E of beta is orthogonal to W. Then beta minus E of beta belongs to W perp. Okay, this vector goes to W perp by the definition of complement. Okay, orthogonal complement. Hence, beta minus E of beta belongs to W perp for all beta belongs to V. Okay. Now, define a mapping from H from V to W perp by H of beta is equal to beta minus E of beta for all beta belongs to V. Okay. Define a mapping H from V to W perp by H of beta is equal to beta minus E of beta for all beta belongs to V. Obviously, H is well defined due to the uniqueness of best approximation E of beta by vectors in W. Okay. So here the H is well defined and well defined function because the uniqueness of best approximation E of beta, okay, by beta by vectors in W. Now to prove that the mapping H is orthogonal projection of W on V per W per. Okay, we have to prove that the mapping is H is orthogonal projection of V on W per. Now, for that, it is sufficient to prove that for any arbitrary vector beta belongs to V, a vector H of beta is the best approximation to beta by vectors in W per. Okay, for this, we have to prove this thing. The mapping H is orthogonal projection on V. Okay, this mapping is orthogonal projection on V on W per of V on W per. It is sufficient to prove that for any arbitrary vector beta belongs to V, a vector h of beta is the best approximation to beta by vectors in W per. Okay, that is by first statement of previous theorem, it is sufficient to prove that beta minus h of beta is orthogonal to W per. Okay, by beta minus h of beta is orthogonal to W per. For any vector gamma belongs to W per, it implies that gamma inner product of gamma alpha is equal to 0 for all alpha belongs to W because gamma belongs to W per. Hence, the inner product of gamma alpha is equal to 0 for all alpha belongs to W. Hence, alpha is nothing but E of beta. Therefore, gamma inner product of gamma and E of beta is equal to 0. Okay. Hence, B minus H of B, E minus inner product of B beta minus H of beta and gamma. By linearity property, we can write beta and gamma, inner product of beta and gamma minus inner product of H of beta and gamma. Okay. Hence, we can write like this: B beta into gamma, sorry, inner product of beta and gamma minus inner product of beta minus E of beta into gamma and gamma, where the value of H of beta is nothing but beta minus E of beta by the definition of H. Okay, the inner product of beta gamma minus inner product of beta gamma plus inner product of E of beta and gamma by linearity property we can write like this. Okay, which implies plus and minus get cancelled, which is equal to inner product of E of beta and gamma. Okay, which is equal to 0. Why? Where E of beta belongs to W and gamma belongs to W per. Okay. Hence the inner product of these two terms is 0. Okay. Hence inner product of B of H of beta with gamma is equal to 0. Hence gamma, since gamma belongs to W per. Okay. This shows that the vector beta minus H of beta is orthogonal to W per. Okay, this is the vector is orthogonal to W per. Then H of beta is the best approximation to beta by the vectors in W per. Okay, hence H of beta is the best approximation to beta by the vectors in W per. That is, beta minus H of beta is the best approximation to beta by vectors in W per. Hence, the mapping beta to beta minus E of beta is orthogonal projection of V on W per. Hence, the mapping beta to beta minus E of beta is orthogonal projection of V on W per. Okay, this is the proof of the theorem. And the next theorem is that let V be a finite dimensional subspace. Okay, sorry, let W be the finite dimensional subspace. Okay, of an inner product space V. Then, and let E be the orthogonal projection of V. Then E be the, let E be the orthogonal projection of V. Okay, on E be the orthogonal projection of V on W. Then E is an idempotent linear transformation. Then E be the idempotent linear transformation of V on W. Okay. Then W per is the null space of E and V is equal to W, direct sum of W and W per. Okay. This is the statement of the theorem. Okay, let W be the finite dimensional vector space subspace of V. Okay. Let W be the finite dimensional vector subspace of inner product space V and let E be a orthogonal projection on V on W. Then E is an idempotent linear operator, linear transformation on V on W of V on W and W per is the null space of E and V is equal to direct sum of W and W per. Here the W per is there. Okay. Now proof. Let W be the finite dimensional subspace of inner product space V, IPS V. Let W be a finite dimensional subspace of IPS V and E be the orthogonal projection of V on W and E be the orthogonal projection of V on W. Then for any beta belongs to V, the vector E of beta belongs to W. Okay. So we know that the orthogonal projection E on V on W acts as an identity operator on W. Okay, so any orthogonal projection E on V, the acts as an identity operator on W. Okay, so E of beta is equal to E of beta for all beta belongs to V. Okay, projection means E square is equal to E na. So here the E square is equal to E. E of beta is equal to E of beta for all beta belongs to V. So E square of beta is equal to E of beta. That implies E square is equal to E. Therefore, the E is idempotent transformation. Okay. Now we have to prove that the E is linear transformation. Okay. Here we prove that the E is idempotent. Okay. Now to prove that the E is linear transformation. Let alpha beta belongs to V be any vectors and C be any scalar. Let alpha beta belongs to V be any vectors and C be any scalars. Okay. Thus, by definition of orthogonal projection, the vector E of alpha, E of beta belongs to W are the best approximation to alpha beta respectively by the vectors in W. Okay. Thus, by the definition of orthogonal projection, the vectors E of alpha and E of beta belongs to W are the best approximation to alpha beta respectively by the vectors in W. Okay. Hence, then the first statement of the previous theorem, the vectors alpha minus E of alpha and beta minus E of beta are orthogonal to W. Thus, E of alpha minus E of alpha is belongs to W per and beta minus E of beta belongs to W per. Why? Because they both are orthogonal to W by previous theorem. Hence, W per is the subspace. Since W per is subspace, then the vectors C into alpha minus C of alpha plus beta minus C of beta belongs to W per. Why? Because W per is a subspace. Hence, C alpha plus beta minus C into E of alpha plus E of beta belongs to W per. Okay, that is the vector C alpha plus beta minus C into E of alpha plus E of beta is orthogonal to W, where C alpha plus beta belongs to V and C into E of alpha plus E of beta belongs to W. Again, by the first statement of the previous theorem, C alpha plus beta minus C into E of alpha plus E of beta must be what? Belongs to W, okay, which implies this vector is perpendicular to W, okay, C alpha plus beta minus C into E of alpha plus E of beta, which is perpendicular to W. Hence, C into E of alpha plus E of beta is best approximation to C alpha plus beta by the vectors in W, okay, but C alpha plus beta belongs to V. Okay, then by the definition of orthogonal projection on E, the vector E of C alpha plus beta is the best approximation to C alpha plus beta by vectors in W. Okay, thus the vectors E of alpha plus E of beta, C into E of alpha plus E of beta, and E of C of alpha plus beta are the best approximation to C alpha plus beta by the vectors in W. Okay. Hence, by the uniqueness of the best approximation, we have C of E of C alpha plus beta is equal to C into E of alpha plus E of beta. Therefore, the orthogonal projection E on V on W is idempotent linear transformation. By the property of linearity, this E on V on W is idempotent linear transformation. Now, next we have to prove that the nullity of E is nothing but W per. Okay. The nullity of E, N of E is nothing but nullity of E is equal to W per. Since any vector beta belongs to V, there exists a unique vector E of beta belongs to W such that beta minus E of beta belongs to W per. Okay. Since any vector beta belongs to V, there exists a unique vector E of beta belongs to W such that E B minus E of beta, beta minus E of beta belongs to W per. Okay. So let beta belongs to nullity of E, which is subset of V. Then there exists a unique vector E of beta belongs to W such that B minus E of beta belongs to W per. Okay. But B belongs to nullity of E, which implies E of beta is equal to 0. So beta minus E of beta is equal to beta minus 0, which is equal to beta. Hence, it belongs to W per. Hence, beta belongs to nullity of E. It implies that beta belongs to W per. Hence, nullity of E is subset of W per, which give the equation number 1. Okay. Let now we have taken the element from W per. Now we have to prove that that element goes to nullity of E. Okay. So beta belongs to W per be any vector. Okay. Then by the definition of W per, the beta inner product of beta and alpha is equal to 0 for all alpha belongs to W. Okay. So since W per is subset of V, okay, then beta belongs to V implies there exists a unique vector E of beta belongs to V such that E minus E of beta minus E of beta belongs to W per. Okay. Hence, beta minus E of beta with alpha inner product is equal to 0 for all alpha belongs to W. Hence, the beta minus E of beta with beta, the inner product of beta minus E of beta and E of beta is equal to 0 for E of beta belongs to W. Okay. So inner product of beta and E of beta minus inner product of E of beta and E of beta is equal to 0 by linearity property we can write like this. Okay. So but this is the 0 minus inner product of E of beta and E of beta becomes 0. So it implies that inner product of E of beta and E of beta is 0, which implies that the property number, second property, non-negativity property, it implies that E of beta must be 0 by the property of inner product space. Hence, it implies that beta belongs to nullity of E. Hence, we taken beta from W per, which goes now the beta goes in nullity of E. Hence, W per is the subset of N of E. Give it as equation number 3. Hence, nullity of E is equal to W per from 1 and 3. Now, we have to prove that the V is equal to direct sum of W and W per. Okay. Now, any vector beta belongs to V can be expressed as beta is equal to E of beta plus beta minus E of beta. Plus minus get cancelled and beta is equal to beta. Here, any beta we can write like this. Okay. Where E of beta belongs to W and B minus E of B belongs to W per. Then B beta belongs to W plus W per. So any beta we can write like this in the form of W and W per. Okay. Hence, V is the subset of W plus W per. But obviously, there is no need to prove this. Okay. Since W and W perp are the subspace of V, then obviously W plus W perp is also subset of V. Hence, W is equal to W plus W perp. Now, we have to prove that this sum is direct sum. It remains to prove that W intersection W perp is singleton 0. Okay. For uniqueness, we have to prove that for the direct sum, we have to prove that W intersection W perp is singleton 0. Okay. So let alpha belongs to W intersection W per be any vector. Okay. Then alpha belongs to W and alpha also belongs to W per. Hence, but alpha belongs to W per implies that inner product of alpha beta is equal to 0 by the definition of W per for all beta belongs to W. Okay, since it implies that inner product of alpha alpha is equal to 0, since all alpha belongs to W, then alpha must be 0. Hence, therefore, the W intersection W per is 0. We taken alpha from W and W per. Now the it comes as W is equal to alpha is equal to 0. Therefore, W intersection W per is 0, singleton 0. Hence, V is the direct sum of W plus W per. Okay. Corollary. Under the condition of the theorem I minus E, under the condition of theorem I minus E is the orthogonal projection on V on W per, it is an idempotent linear transformation of V on W per. This is the most important. Okay. With null space W. For this orthogonal projection, null space is W. Okay. And this is the idempotent linear transformation of V on W per. Okay. Hence, the today's lecture, we seen that what is the orthogonal complement and some theorem on this. Okay. So in the next lecture, we will continue. Okay. So anyone who have doubt, they can ask me on WhatsApp. Okay. Thank you.